Thank you very much for joining this webinar. Nazarbayev University is setting up series of seminars, webinars now online on different topics, including those and research. So as I propose to talk about the advanced batteries for next generation applications, because I think the batteries are very important in our life. It's not the most important, but one of the important things in our life. Okay, so here is a topic. My name, I'm Professor Zhumabay Bakenov from Nazarbayev University, and the research I will talk is conducted at Nazarbayev University in different places like School of Engineering and Digital Sciences, where I work, National Laboratory Astana. There are three logos, and also Institute of Batteries. Institute of Batteries is our startup company, which was established in the end of 2013. And because this is Institute of Batteries, it works mainly with batteries. About myself, I got my doctorate degree from Tokyo Institute of Technology, and also have PhD from Kazakh National Academy of Science. And I had experience of working at university in Kazakhstan, and also was working at Tokyo Institute of Technology, which is Tokyo Tech, and University of Waterloo in Canada. Mainly, my research is about materials, new materials for energy, on batteries, and also we are doing the research on the other applications of materials, which includes electrochemistry, like electrochemical sensors, electrochemical catalysis, electrochemical catalysis, synthesis of various materials. And we have very good collaboration with many countries, with many research groups worldwide. So today I want to talk about why we need batteries, some general things about batteries, and how to invent the batteries, and the research what we are doing at Nazarbayev University, our battery group. So why we need batteries? I think it's not necessary probably talk about that, because now each of you have at least one battery, right, with you. It's your cellular phone and portable computer, whatever, many other things. Your watch also has batteries now. I think now not many people are carrying mechanical watches, mainly electrical. So all are powered by batteries. Also, the wide implementation of batteries is demanded by the problems we have now. Here in this slide, you can see we have limited amount of fuel, what's called fossil fuel, burning fuel to provide the energy, electricity for our needs. Also, the use of fossil fuel leads to the pollutions. So we have two large global challenges, issues is energy and environmental issues. So to address them, to solve them, now we have to introduce a lot of renewable green energy, which are like wind energy, solar energy, and so on. Also, a lot of pollution is coming from from the transport. Therefore, we have to think about the ecological transportation, like electrical transport, electric vehicles. So those all need batteries. And in this slide, you can see the integration of different energy sources. We cannot immediately stop all the traditional energy sources like thermal energy, and we have to combine all of them, integrate all of them, and to provide the quality, high quality energy supply for our needs, to power everything we have. So for that, this very different sources of energy should be combined together into the, we call it electrical grid. Now the electrical grids getting smarter, they're controlled by computers, and then this integration of this kind of sources can be controlled and can be managed. In the heart of this integration, because of the intermittent nature of the renewable sources, like wind is not always blowing with the same speed and not always blowing, and sun, solar energy we can produce only in daytime. Therefore, they're kind of variable energy components. Therefore, for the integration into the grid, we need batteries. We have to store them, and then, for example, daytime charge the batteries, and nighttime release the energy to the grid for its high quality consuming and production. And therefore, the market done if it is profitable. So the market is of the energy storage is very huge. So now the energy storage market is exceeding $200 billion per year. So it's, you can imagine, is almost say GDP of Kazakhstan. In this market, the battery energy storage is playing a critical role. And the application of the batteries is really wide. So here you can see different pictures of different electronics, which are all powered by batteries. Some of the photos here are coming from our lab. Some of them are from internet. And then there is a requirement for battery performance because now in the left side picture you can see a so-called Moore's law graph. The electronics getting smaller and smaller. Here you can see from the large computers, there were even larger computers before that. And then now we are facing a very rapid miniaturization of the electronic appliances, devices, and therefore we need smaller batteries. But the batteries, even they get smaller, they have to provide enough energy to power such electronics. And also here you can see a photo of electrical vehicle. It's a hybrid one, BMW 7. And there are a lot of other applications. So the batteries are ranging from very small to large one, and the chemistry also is varying. Somebody's coming, joining the webinar. And there are a lot of chemistries in battery, different types of chemistry. So the largest one is a lead acid batteries. Probably many of you saw that kind of batteries. Those are used as mainly as starter batteries for cars. Each car with internal combustion engine, and other cars, they have at least one lead acid battery to start the engine. Also, there are other types of batteries, which we also call them accumulators. Right? So, along with lead acid batteries, there are lithium-ion batteries, nickel-cadmium batteries, nickel-metal hydride batteries, and other type of batteries. And the battery market on the right bottom corner, you can see the distribution of battery market. So largest sectors of where the batteries are used are automobile batteries for electrical cars, and electronics, portable electronics, and industrial batteries. In industry, there are a lot of electricity energy backup systems, which are also using rechargeable batteries, accumulators. So if we talk about history of batteries, there were famous experiments of Galvani in the 18th century when he was studying the dead frog's legs, and when touching them by different pieces of metals, he observed the contraction of the legs of muscles of the dead frog. And gradually, during the experiments, it was discovered that when you are having two different metals in the electrolyte, which is conductive media, then you can find a potential difference, voltage between these two metals, and you can use this to power to produce electricity. So in the bottom picture, you can see a battery. It's a pile of electrochemical elements which were constructed by Volta. I had a chance to see this in the Volta Museum in Italy. So this was, as you see, long ago. And the development of batteries can be shown through this graph. So there is one jar or urn which was found in 1930s, which is aged like 250 BC, which looks like similar like a battery. So some of the scientists, they consider this as the first battery. So the batteries are really very old. They have very long history. So in this graph, you can see different types of batteries which were developing. And finally, now we are mainly dealing with the lithium-ion batteries. So the lithium-ion batteries, which are started in 1980s, commercialized. And you can see various types of batteries coming from there very long ago. Okay, here you can see the major players on the market batteries. These are lead acid batteries, nickel cadmium batteries. Later they were like in parallel developed with the nickel metal hydride batteries. And this is the iron batteries, which were invented by Edison. Probably you know Edison, right? Although these two previous names are not very familiar to everybody. And for again development of batteries history, you can see from this picture this was a kind of telephone, radio phone used in military. You can see how huge it is. Then the sizes of telephones started reducing, make them lighter, and even though they were lasting long, because batteries were developing in parallel to power this, because we want to use our telephone at least during the day, right? Before we have to charge them again. But recently I observed that the telephones are again getting bigger. So now this is iPhone 12, is getting bigger than iPhone 3, I believe. Maybe thinner, but the screen is larger. So the screen is consuming a lot of, the display consuming a lot of electricity, so batteries should be having more energy density to power them longer. And what else to show here? When we talk about batteries, we have to consider the energy density. So energy density means how much electricity we can store per gram of battery or per cubic centimeter or per volume of battery. So here you can see the energy density of battery is growing.
Чисто слушаю, то не получается. Давайте подожди. Просто чтобы было.
Okay, and then you can see the energy density of batteries are growing, starting from the lead acid batteries, which had only 30 watt-hour per kilogram. So 1 kilogram of such battery could store only 30 watts per hour, and then it was growing, and currently we have the batteries which can have energy density about 1,000 watt-hour per kilogram. Those are still on research and development stage batteries. So if you talk about batteries, they are divided into two types. Probably you know some of them are called primary batteries. They cannot be recharged. They are one-time use, non-rechargeable, because the chemistry inside is non-reversible. So the reaction goes one direction when you're using the battery, and when you try to charge it, the reaction cannot go back. Okay, it can be partially reversible, but it's very dangerous to recharge primary batteries. It can damage. And then there are rechargeable batteries, which we call accumulators. So we are mainly working with rechargeable batteries because rechargeable batteries are more convenient, they are more ecological, and so on. But comparing with the primary batteries, rechargeable batteries, they need more work because we have to find a reversible reaction. When you charge the battery, the reaction which is happening inside should be completely returned back, should be reversed. And among current batteries at the market, we can name 3 types of batteries: nickel-based batteries and lead-acid batteries. We talked about them. Here you can see the reactions happening inside the batteries, and lithium-ion batteries. So we mainly working with lithium-ion batteries. So here you can see the chemical reaction of this battery. This battery is having the highest voltage potential. So these batteries, currently we have new type of batteries, lithium-ion batteries, which can provide up to 5 volt potential. So combined with the current, it gives very good power to power various applications. And why this battery is called lithium-ion batteries? Because in the reaction here you can see there is a lithium ion, which is when it's charged, it's extracted from the electrode, from the cathode, and then when it's recharged, the battery, then discharged, then it's inserted back into the cathode material. And that is a very highly reversible reaction. Therefore, we can use a lot of energy compared with other types of batteries. And next slide, you can see how the battery works. So it's kind of, we call this kind of batteries, lithium-ion batteries, we call them as a rocking chair battery, because when the battery, lithium-ion battery charged and discharged, now it's showing discharge, now we'll show charge direction. The lithium ions, they're extracted from one electrode and inserted to another electrode. So there is no any gas release or precipitation of any other additional reactions. Of course, they're happening in the very small ratio if a battery is operated correctly, properly. Okay. Later, I will show you the cases when the battery is operated not normally. It's very dangerous. So lithium-ion batteries, they are very convenient, and therefore they power most of our electronic gadgets and electric vehicles. Currently, lithium-based battery, they're starting occupying the market for storing renewable energy. And probably you saw, along with the cars, for example, Tesla company produces household electricity backup systems. They look like a large smartphone, which is installed on the wall, and then it can store the energy nighttime, because nighttime electricity is cheaper than daytime, and storing nighttime and using daytime. And these batteries are good because they have high voltage, high potential. As I said, it can reach 5 volts. They are very stable in cycling. There are batteries with thousands of cycles, and you know, from your mobile telephone, you can charge it every day for new telephone, once a day, and 365 days a year, and you can do it repeatedly with almost no loss of capacity. And after 1 year, it starts degrading. But for other types of batteries, you cannot do the same with other types of batteries. They will die earlier than lithium, much earlier than lithium-ion batteries. These batteries have a high energy capacity, so there are no other batteries which can compete with lithium-ion batteries in the capacity. They are small, and the geometry of these batteries are very flexible. You can see here on this picture the applications. They're of different size, and you can make batteries of various geometry using lithium-ion technology. And these batteries, after charging, they stay charged very long time, so they have low self-discharge. So comparing with other batteries, they are best for the self-discharge. So the lithium-ion batteries, they produce in various shapes. So you can, the cylindrical batteries like this, right? The Tesla cars, they're using this kind of shape. Prismatic batteries and pouch cell batteries, they're similar to each other. And prismatic and pouch cells, they are used by electric vehicles by Japanese car makers. So like Toyota and Nissan, they're using mainly prismatic and pouch cells. The advantages of each shape depend on the application. And if you see inside the battery, it's a really complicated system. This slide shows like schematically simplified description of the battery. So here at the top left, you can see the roll, which consists of a separator, anode, and cathode, and then it's inserted in the can, in the casing, which is filled with electrolyte. So previously it was liquid electrolyte. Currently, most of lithium-ion batteries are lithium-ion polymer batteries. So they're using polymer electrolyte. And when on the right side, you can see the for one of the chemistries of lithium-ion batteries, the contribution of the materials cost for each battery. And here in the bottom, you can see a kind of structure of prismatic cell. So this is Tesla model, I believe S, or newer one, I don't know. And then this battery now, this car may run up to 430 kilometers per one charge. And if we see inside the battery, batteries for Tesla made by Japanese company Panasonic. So the type of battery, geometric type is 18650, where 18 is the diameter of the battery, and 650 is the length of battery. And then one Tesla car has more than 7,000 such cells, which are combined in the battery modules like this. So you can see so many batteries inside. As I mentioned, lithium-ion batteries, they have very high energy density. And in so many batteries, there is only 7 kilograms of lithium contained in these batteries. So this is the internal structure of a pouch cell, or similar to the prismatic cell, which are used, for example, in Samsung. You probably heard about the accident with the Samsung Galaxy 7, right? Several years ago, there were problems with batteries, and Samsung was forced to call back a lot of such electronics to replace the batteries. And here you can see also, there should be video. Oh yeah, it's moving. There are different types of explosion of the batteries, so this different devices. And here on the bottom left, you can see a person running because the electronic cigarette is start burning itself suddenly in his pocket. So it's another danger of smoking. And the right bottom picture, you can see it's a robot which was just prepared to load for transportation to be launched to space, and suddenly it started burning because of construction of lithium-ion batteries. So lithium-ion batteries, because they have high voltage and they have organic components inside, they're dangerous if misused or short-circuited, for example, overcharged, overheated. So therefore, the use of lithium-ion batteries should be very careful, with big care. So how to invent and develop a battery? So developing batteries schematically is very simplified way. It's not that complicated. So here you can see so-called lemon battery. You got a lemon and two pieces of two different metals, say copper and zinc, for example, insert to the pin into the lemon, and you can use the electricity produced between these two electrodes. You can select the electrodes to have higher voltage. I will not talk about that here, but there is a so-called table of electrochemical potentials of different metals. You can choose two metals with larger potential difference between them, and you can get a battery with higher potential. Okay, so and then you can use it to power, for example, light. And here at the bottom, you can see a picture where the one cell is shown. It's one cell means only two electrodes, one anode, one cathode. And you can combine these single cells into a battery stack or battery. So this is cell, this is battery or battery stack. So you can combine them in parallel or in series, depending if you want to have a stack with higher voltage or higher electrical current or power. Oops. And in reality, the development of battery is not easy. So you have to search for good materials to have a stable chemistry and reversible chemistry if you're talking about a rechargeable battery accumulator. And then test them, modify them, make them more chemically and electrochemically stable. Further test them in batteries and then combine them with different electrolytes and so on. There are a lot of things, a lot of works within these green and blue boxes. And finally, you can go to commercialization. Commercialization of batteries is very risky and it's not easy because if a large company like Toyota, for example, or Tesla start commercializing a very interesting battery, but a very new one. And if the system was not studied very well and very deep, there may be some problems. And then it will cause a lot of money loss for such companies. This is a famous chart presented by the battery stars Tarascon and Armand in Nature journal in 2001. So it shows how to choose materials for electrodes for batteries. So to have a larger potential difference, we have to choose a battery electrodes for the cathode, the one which is as much as higher in this chart, and for anode, the one which is lower here. So because on the vertical scale, we have potential versus lithium electrode. So, for example, if you combine the most top one with most bottom one, you will have the potential difference about 4 volts. But also, when choosing the electrodes, we have to think about the capacity, energy capacity. So, on a horizontal scale, you can see the capacity. So, it's better to combine something like in the right top and right bottom of this chart to have a high potential battery with a higher energy density. So the best anode for batteries should be lithium because it has the lowest potential among all known metals. And then the positive electrode, you can use whatever the materials here. Because capacity is given per weight per kilogram. We can combine 1 kilogram of lithium with less amount of say lithium manganese metal oxide at the top left corner, and then you can have a good battery. So this cathode in red and anode materials for lithium batteries. So creating batteries is selection of 2 electrodes with sufficient potential difference, and select an electrolyte, which liquid or polymer media between 2 electrodes, and that should not decompose when you're using the battery, otherwise, or should not burn when you're using battery. Therefore, selection of electrolyte is very important and should be very conductive. Then you can charge your battery quick. So you probably heard about batteries reported in the news that they can be charged in 1 minute, 1 hour, and so on. And then you have to assemble the battery and start testing, optimizing the battery. So here, the list of problems we face when we are what we have to do when we are selecting the materials for batteries. For example, if you choose two electrodes and there is electrochemical reaction which evolves gas products, so that's acceptable in some cases, but dangerous because if it is sealed battery, there could be pressure build up in the battery and then explosion of the battery. So these are the part when I will talk about what we are doing for batteries in our group. Here in the picture, the next slide also. 1 second. In further slides, we can see those also. So here you can see some of batteries we made. Some of them on the right top, you can see so-called power banks. These are 2 ampere batteries, power banks. So you can charge one time your battery. It sizes like lipstick. And on the bottom, you can see some pamphlets we produced describing our batteries. And the cylindrical battery, the pink one, which is inside of these power banks. Also a so-called button cell, coin cell, which was used in the keys for cars and power them. This is the pouch cell we made. This was used to be tested with a drone, a quadrocopter for with military people. And this is the this is not rechargeable, but it's primary. The chemical reaction is irreversible. You can only use one time. You cannot charge. These batteries were used for alarm system for signalization at the border in Kazakhstan. So today, just taking the photos of our labs, just to show you what we have. Is a brand new laboratories. On the left side top, you can see the room for testing. I can enlarge it, but in general, this room consists of battery testers. So we can test different sizes, different shapes of batteries. And we have, I don't know exactly, several hundreds of channels, we say, in battery tests. So in the same time, we can test several hundreds batteries. And there are boxes which can, we call them temperature boxes. So this, for example, one can, it's a kind of refrigerator. So it can maintain temperatures from -70 degrees Celsius to 100 degrees Celsius. So we can test the batteries inside, simulating different weather conditions. For example, Astana, -70, from -20 to -50 in the winter, and also summertime, or using electric vehicles or starter batteries in cars. They have to survive for temperatures up to 100 degrees Celsius. And left bottom here we are. This is the laboratory to develop electrolytes. So I have colleagues who is working with polymer electrolytes, for example. And near window there is a small box. That's a very important one. Is called electrospinning. So using this equipment, my colleagues are doing development of polymer membranes. They're making microfibers, which are then combined and making membranes like separators of polymer electrolytes for batteries, for fuel cells and so on. And the right picture, you can see 2 glove boxes. You can see gloves here, right? This box has 4. This one also has 4, but they are very different. The left one is 2 assembled batteries, coin cells and so on, button cells. And in the center, this one this is very complicated and very sophisticated glove box. It has so-called magnetron spatter inside. Magnetron spatter can evaporate various ceramic materials, oxide materials, and so on, and evaporate and deposit them on the various substrates. So, and the further part of this glove box has a so-called thermal evaporator. Magnetron is using radio frequency waves to evaporate materials, and the thermal evaporator uses temperature. So here in this glove box, we can assemble so-called micro batteries or thin film batteries. We can evaporate and deposit anode or cathode, and then deposit solid electrolyte on surface, also evaporating some material here inside, and then deposit the second electrode, and then assemble a battery. So here we are working with the micro or thin film batteries. And here you can see in the right picture some kind of furnaces. We have a lot of different types of furnaces, not shown here, where we synthesize the material. This is the slide showing one of our social projects when we developed electrical wheels for wheelchairs for handicapped people. So we were making these wheels for people together with some sponsors. And you cannot imagine so many people in Kazakhstan need such chairs. Now 150,000 people in Kazakhstan, more than, need wheelchairs. And 30 of them cannot use mechanical ones. They have to use electrical ones due to health conditions. Our battery group, we established our group in 2011 when Nazarbayev University was open. From that time, since that time, we received a lot of projects from different sources. It's the government of Kazakhstan, one of the main funder of our research, then World Bank, European Union, British Council, Government of Japan, Nazarbayev University, national and private companies. We have a lot of students participating in our projects, not only Nazarbayev University, but from other universities like KazNU, KazN2, Satpayev University, Gumilev, Kazakh Bridge Technical, Kargu, and we got students in summertime coming from other countries, also like Korean, Russian, and Chinese universities. We have very strong collaboration, especially with Chinese universities in that term. We have our startup company, which is called Institute of Batteries, as I mentioned. We have totally more than 300 square meters labs for batteries. And currently we are running the projects totaling about $3 million for 3 years, so like $1 million per year. This is not one project. We have about 15 projects there. So therefore, each of them is small, but when we combine all together, it looks like large funding. Since opening our group, we finished about $15 million projects. And we are publishing a lot. Since 2011, we published now, I think, 140 or 150 papers in very good journals. So please come join us, and you will learn a lot from us. This is our group. Now, this is not whole group. It's some of those who has doctorate degree. So these all doctors here, and they got their doctorate degrees from different countries. Here we have Dr. Zhang. Now he's in China. He's a big professor in China. Indira, Tokyo Tech, Al-Farabi University, Chungnam National in Korea, Imperial College, Dr. Ader is a faculty professor at Nazarbayev is working with us. Tokyo Tech, Morocco, Sejong in Korea, Florida from US, Sandovash got her PhD last year in Marmara University in Turkey. These are our group also. Here our good visitors. In that picture, you can see Professor Sung-So Kim. He's my lab mate in Japan. He used to be a senior technical officer at Samsung SDI and developing Samsung batteries. Now he's professor in Chungnam National University in Korea. Here you can see Rashid Yazami visiting our lab and riding horse in Almaty. He was one of the inventors. There were 4 inventors of lithium-ion batteries. You know, in last year, 2019, 3 of them got a Nobel Prize, because Nobel Prize can be given only to 3 people. And this is one of them, Dr. Yoshino. I met him last year at the conference in Japan. These are our students abroad who is doing PhD. Some of them already got. You can see the titles: Dr. Umirov, Dr. SEDS Fall, and some of them doing their PhDs in other countries like Japan, France, US, Korea, Russia, and the US. These are our partners, the logos of many universities here from different countries and continents. These are companies we are working, collaborating, also from different countries, from Japan, Europe, China. And about research, I'm talking 40 minutes already. So we are mainly working on batteries. We are doing other things also, but today I'm talking only about batteries. So for that application for batteries, we are developing a lot of new materials. We call them functional polymers, catalysts, and electrode materials, and so on. But the way we prepare these materials and their testing can be applied for other areas like water splitting. Water splitting now become very popular in the world to produce energy. So we split water, you know, H2O is split to hydrogen and oxygen, and hydrogen become a very good fuel because it's very ecological. When hydrogen burns, it produces only water. So it's very, yeah. Oh, I forgot to say, if you have questions, there is Alman Suragishev wants to ask questions. So please go ahead. You turn your microphone first.
Sorry, I have misclicked this one button. It was occasionally pressed.
Okay. So you don't have question?
Yeah, I just misclicked it.
Okay, no problem.
Hello, Professor. I have a question.
Yeah. Yes, please.
So on slide 19,
okay.
Yes, it's me. So on slide 19, you told us about 3 types of lithium-ion batteries, right? So can you please say the difference between pouch and one started, and prismatic one? Mm-hmm.
Yeah, let me go back in. Then others will understand what this one. So
yes,
here,
yes.
Yeah, in prismatic cell, mainly okay, so pouch cell is similar to the cylindrical one. Okay, so the cells consist of long cylindrical battery. Okay, but made in form of flat one like this.
Okay.
Okay, and here in the prismatic, but they can be done in both ways. But mainly in prismatic batteries, the electrodes they cut. Okay, in the piece set in parallel, each of them rolled with the separator. So the separator is rolling, and electrodes inserted between the waves of separator. Okay, and then they connected with each other, the electrodes, and that depends on the application. What you want to get as a if it is high power, means higher electrical current should pass through the battery. You want to power the electric motor, then you have to have a less resistance, electrical resistance. The electricity should pass very quick, because power is, when you're powering something, it means there's a high electrical current. Okay. For the other applications which doesn't need that high power, that means they can work at the low electrical current, then the resistance is not that very critical. Okay, so depending on that, you choose the shape of the battery, and of course it depends on the material also. What kind of material you're using in the battery? Okay.
Okay, I got it. Thank you.
Mm-hmm. So where we are? Okay, here. So the main types of batteries we are working on are lithium-sulfur batteries, rechargeable aqueous batteries, thin film batteries, and also we are working for development of new materials. We're using new sources, for example, in the bottom here, this beans with something brown is rice husk. We're trying to make carbon material from them, developing various polymer materials, polymer electrolytes. Here, for example, in the center of the brown roll, it's a bendable, flexible material for batteries. Okay. And I will talk a little about each of those. I have a bit time. So first is aqueous batteries. Aqueous batteries are the system is very similar to lithium-ion battery, like a common one. But here, comparing with the lithium-ion batteries, we are using aqueous electrolyte. Okay, you saw the pictures above when the batteries are burning, lithium-ion batteries. Here, the battery cannot burn because it doesn't have anything burnable. It has water inside. So even you try to burn it, it will not burn. Okay. But comparing with the organic electrolyte in the usual lithium-ion batteries, aqueous batteries, water has lower stability, and it decomposes if you try to make a battery with a potential higher than 2 volts. Okay, the water stability is a restriction for this battery. But otherwise, this battery is absolutely safe. There is no any flammable materials inside, and this battery is ecological. We are using zinc anode, environmentally friendly cathode material, lithium manganese oxide, and aqueous electrolyte. Of course, you cannot swallow this battery. Still cannot swallow because it has potential difference. It's very dangerous. But in general, this is very friendly, ecologically friendly and safe battery. Okay, this battery is 2 volt, and using all this well-developed materials like lithium manganese oxide is produced in 1,000 tons by a battery industry, and zinc. Zinc is also a very abundant product of industry. And we could develop a battery. Here you can see a graph showing C rate charge and discharge of battery. 60 Siemens, the battery charged in 1 minute and can be discharged in 1 minute. Okay, 30 C is 2 minutes, and so on. So the 60 divided by this number gives you the number of minutes you charge and discharge the battery. So the battery can be charged in 1 minute. I think it's very good. This is the same battery when you are charging, discharging at different currents and different lengths of charging and discharge. Finally, you come to the very high current. It's almost short-circuiting the battery. And then when you, after charging and discharging at this C rate, so like 1 minute charge, very high current, very quick battery charge. And after that, you return back the same battery to lower current. It's like 10 hours performs as a new battery. So this battery is very stable, is not damaged by that current. When you're charging your batteries very quick, it means you're applying very high current. That's very dangerous for chemistry inside. So battery which is quickly charged and discharged, now new iPhones has that option, right? That means that you are damaging your battery. Whatever the maker says, be careful to charge battery fast. Better to charge slowly, then you will have your battery lasting longer. So this is the prolonged tests of this battery. 6C means 10 minutes charge and discharge. Battery is operating very stable, over 300 cycles. So it's like if you charge the battery every day, it's 1 year operation of the battery. And the capacity loss is not much, less than 10%. And the green line shows so-called efficiency. So is 100% energy could be extracted. So you extract amount of energy, electricity, you can extract 100% of that. So the battery has very good efficiency. Lithium-sulfur batteries, now they are considered as the best batteries in terms of capacity, because these batteries, now this is data what we have in our lab, but theoretically, which we also could do in our lab, these batteries are 10 times higher energy capacity than commercial batteries. So if like Tesla now runs 400 kilometers per one charge, if we make lithium sulfur batteries of that the same weight, then the Tesla will be running theoretically 3,000 kilometers per one charge. But now we have, because that is slow charge and discharge, to have a what's called acceptable current for charge and discharge, rapid, relatively quick charge and discharge, then we could double the capacity of the battery. So if we insert this battery into a Tesla or another vehicle, electric vehicle, then it will run 2 times longer range and per charge. And why lithium sulfur batteries? Also, along with the capacity, sulfur is very cheap. So like this picture is from the west part of Kazakhstan, I believe. There's a deposition of sulfur which is coming from oil. So it's creating a lot of problems. We have to store the sulfur, and it is taken by wind and creating ecological problems. And the oil companies, they are ready to give it for free, while for the cathode materials in current commercial batteries, you have to pay a lot of money. And the preparation is very simple. We mix sulfur with ketchum black. Ketchum black is carbon, which is produced by Ketchum Black International in Japan as a tire filler. So when they produce tire, the carbon is the main part of the tire. So we mix them and add polyacrylonitrile, which is polymer, conductive polymer, heat at 300 degrees Celsius, and then we get the cathode material for sulfur batteries. So we could make this kind of batteries. This is 10 ampere battery. It's like in your iPhone, the battery is about 2 ampere. So this is 5 times larger battery. This is our old tests when we are doing safety tests, comparing the polymer we developed. The right side, I think, the polymer electrode which we made, and this left side is the opposite. So the burning one is commercial one. Left side is our polymer electrode. It doesn't burn. Finally, we couldn't ignite the polymer electrolyte we're developing, and the commercial polymer electrolyte just burned away, completely decomposed. This was project with the Nissan Motors, developing polymer electrolyte for Nissan batteries. Also, I mentioned flexible batteries. You can see here. So we made a pouch cell with using our flexible materials inside. Then we bend the cell, and then we roll the cell, and you can see the this lamp is still lighting. So the battery is operating without any problem. I cannot show it today. I didn't include here. We have a video. We cut the battery in pieces and still working. So even ceiling was broken. The battery was cut in half. The lamp is still on. The battery is still operating. This is, we can skip it, just showing the mechanism how lithium-ion is conducted in polymer electrolyte. And finally, for this type of batteries, we are having now currently stopped, but due to COVID, we have tests of these batteries in various applications for storing solar energy, for radio, for quadrocopters, for calculators. We have coin cells. We are using them. These are main equipment we have. This equipment to make these pouch cells, larger batteries. These are other type of equipment we have. Synthesis, analysis, this X-ray diffraction, for example, glove boxes, furnaces. This biologic VMP3 is a blue box here in the bottom right. Important equipment. It can do 75, I think, electrochemical tests. Micro batteries. This is a relatively new topic for our group. So the applications a lot. Currently, the cards, these chips, they're using a lot of information, and currently some cards, they have a small battery inside, and to power this small computer, which is integrated into the card. So development of such small micro batteries is very important also, and applications are many. the medical application here you can see. Okay, and the preparation we are using magnetron sputtering, as I mentioned before. We are evaporating different materials using different energy, for example, silicon, and we are depositing on the substrate, and then we are doing preparing micro batteries. I cannot show everything today. 3 minutes to have 1 hour of my talk. And 3D batteries. 3D batteries, we are making different materials using also magnetron sputtering, other chemical deposition, electrochemical deposition of the materials on 3D materials like this. So you can see as this is the nickel foam, and we deposit first one electrode, then another electrode, one electrode, electrolyte, sorry, and then the second electrode. And we can have a battery which is kind of hidden inside here. So because this metal, the nickel has a very large surface area, we can deposit a lot of material inside. So we can make the battery smaller. So we can have a battery which having same size, but can host a lot of material inside. So this is the SEM, electron microscopy pictures of that materials we are making. And also we are synthesizing so-called classical materials, which are produced by companies. We are trying to improve them. There are some interesting photos by SEM, scanning electron microscope, transmission electron microscopy. These are we are trying to characterize the materials. This 20 nanometer scale here, and you can see this using electron microscopy. We can see how the material looks inside. We have our own conference. We started 2013. This is the first conference. We've got people, colleagues from Japan, Korea, Germany, Canada, China, Turkey, UK, and Kazakhstan gathered together. This year we got our 8th conference, more than 100 people from different countries, but we had it online. Last year it was in Almaty, in Al-Farabi, Kazakh National University. So this 2017, 160 participants. And that's the last slide. If you have any questions and still here, I'll be happy to answer your questions. Here are my contacts. It's easy to find us. It's batterykazakhstan.com. You can go and see what we are doing. We try to update, put our news there. And this is my email address. Thank you very much for your attention. Any questions?
Dear Professor, thank you for presentation. Yes. Dear participants, please ask your questions. And also I want to add that we are recording this webinar. And if you miss something, we will later upload this on our YouTube channel. You can watch it, you can know more. It was really interesting. Please ask your questions.
We still have 90 people. You can ask in Russian if you like. I speak Russian. You can ask in Kazakh also.
Hello, everybody. My name is Aida. Hello, Professor. So I joined a little bit later. Yeah. Dear participants, if you have any questions also about admission requirements, admission to our school, about research life of our school, you can just ask us. Also, we would like to inform you that in the middle of November, we'll have a virtual open house day of our school. There will be in a unusual format. It will be like a forum about innovation, research, startups, about our students' life. So you are more than welcome to participate in it. Yeah, if you have any questions, please ask. Okay, so here is one question. Can you say about commercialization your products?
Commercialization. As I said, commercialization is a very complicated thing. Even you have commercialization needs a lot of not only money, but being very brave about that. Because if any device will be using your battery and there will be a problem with safety of the battery, for example, then the company which is using will be having a lot of problems. You know, there are cases with Boeing's, what was, I forgot the name. Okay, so other companies they had problems because of the batteries. And we are in the stage with the lithium sulfur batteries, for example, at the stage when we close to the era of commercialization. With aqueous batteries, we also, I think the closest technology we are developing to commercialization is lithium-ion aqueous batteries. So these are very safe, and we have patents in US and European Union for this battery. For sulfur, we have only for US patent. We are working with Chinese colleagues, and one of our batteries is produced in China. But we are making them secondary battery, rechargeable accumulator. But because in China everything is much cheaper than anywhere in the world, they're making them primary. So they use it, do not recharge, just dispose and buy a new one. It's about sulfur batteries. They're making coin cells, and probably, you know, in desktop computer there should be one coin cell, coin battery, which powers the watch and keeps the memory of the computer. So they're producing such kind of coin cells in China. Any other questions? Oops.
Okay, if you do not have any questions, so we can just, as Lunar said, that the record of this webinar will be in our YouTube channel. Thank you for all to participating. Take care. See you next time in our next webinars. Thank you, Professor, for this wonderful presentation.
Thank you very much for participation and organizing this. Thank you. Bye.
Thank you.
Bye.
Bye.
Thank you, Professor.
See you.
Thank you,
Bye.
Professor. Bye.